Talk this afternoon will be about using technologies to determine likely crop size for Australia, and I would also acknowledge the team that I've been working with for the last 17 years, specifically Professor Graham Hammer, and in my talk I will also show a brief history of where we started with this work. And first of all, I want an overview of my talk. I will look at the credibility of predictions in terms of weather forecast and also crop productions. We touch on variability, variable environments producers are operating in, evolution of crop statistics, touch on decision support tools that have been developed to actually get a better handle on crop climate variability, increasing the lead time, and also look at the missing link in crop production estimates, and then also linking crop models with general circulation models, and then also touch on new technologies in terms of phenotyping and other in improving breeding trials, cultivars. Credibility and predicting the future has always been at the forefront of many scholars. This one specifically of the 6th century, those who have knowledge don't predict, and those who predict don't have knowledge. I like that. I prefer that one from a Chinese poet. For many people or people, this prediction is mainly just the flip of a coin. They reduce the probability environment into a hit and miss type of approach, rain or shine. But for within the space that I'm operating in, and for crop science and climate science, everything is occurring in a continuum space, and it's very important to take that into account. Weather forecast, seasonal forecast, and climate projections has different predictability, and up to 2 weeks, and also the highest accuracy within 1 week, and then it reduces and then increases the 10 year to 100 years for climate projections. But there's a lot of uncertainty still in that space, in the gray area. This is likely to increase somehow a little bit with technologies improving, but still a lot of the uncertainty will exist in future. For crop forecast, especially early season forecast before harvest, crop forecast is has higher predictability in that space, and this can be increased by using climate forecasts like ENSO or general circulation models. Early civilizations were also very intrigued and very critical for them to know about forewarning of crop production, and the survival of them was dependent on that. Some civilizations cease to exist, and the fact is that when they go back and look at those civilizations, many of those cease to exist due to prolonged droughts or climate variability. When we look at the early settlements in Australia, they were faced with production, cultivating the land. They were faced with extreme weather conditions, highly variable climate at that stage, a lot of uncertainty, and also very high risk of failure. Moving forward into the 20th century, the huge variability still exists at temporal and spatial scale across Australia in terms of rainfall variability. This has a huge impact on the crop production in Australia. This is the wheat production at the national level, time series of that, and the blue line is the yield variability. As you can see from the huge increase in yield, but also in variability from the 60s. And at the same time, while the area of production for wheat in Australia stabilizes, the wheat yield variability kept on increasing. We all know that climate variability is also affected by interannual and decadal and long-term change. which is very critical to actually measure and take into account, and having a system that actually can take these variability different scales into account. Can we do better? Can we predict some of this variability? And Australia is fortunate that, in a sense, that the ENSO, the El Niño Southern Oscillation Index, has a huge impact across Australia on climate. And using this, when we look at us, this can be highly predictable through the ENSO Southern Oscillation Index. This graph here just shows you that when you look at a 20-year running window, and you can see the red line, the frequency of El Niños has increased, while the frequency of La Niñas has somehow decreased. So although there's a huge impact of ENSO, there's also changes that happened from the 1976 onwards. And we've written a paper on that also that can be downloaded from my research space. Producers and households are operating within a highly variable climate environment, complex systems. Many decisions has to be taken for these farmers. Some of them are quantifiable and can be measured, but much of that is also to do with human dimensions and their attitudes towards risk and cannot be measured. Just some background. Farmers, specifically in Australia, are excellent risk managers. They're successful businesses within the world's most variable climate. Climate risk and change is already built into the system, which farmers are adapting towards. And we've developed in QAAFI some of the world's leading regional and point-scale crop simulation models. And this photo here, I've taken that in Emerald in 2006, where a wheat crop, a winter crop, and also a sorghum crop, which is a summer crop. Summer and winter crop are next to each other, ready for harvest. And you can see farmers are already adapting to this climate variability that's already occurring on the farm. It's very critical in science to ask the right questions, because very easily we can have the right answer to the wrong question. For example, Russia bought all USA grain stocks in 1972, and the USA had no forewarning of these huge, what that means to their economy and their crop production when they bought all the USA grain stocks. And Gerald Bungie, the chair of the World Agricultural Outlook Board, mentioned that specifically, and that's where, after that in '72, that's when the World Agricultural Outlook Board was created, because they wanted to know what's actually happening across the globe about crop forecast and crop likely size of crop production. In UQ and QAAFI, we've developed different crop scale models operating at different scales. Probably all familiar with APSIM, which is a dynamic point scale model. My models that I've developed operate at the shire scale, and it's mainly to predict yield and take into account water stress, and operating at the shire or regional scale. Some background on the crop information in Queensland specifically. In the 1947, crop forecasting services mentioned the intention of cropping has to be taken into account. In 1977, the Americans started to use the Landsat, and that was also then started to be mentioned in the crop forecasting services to be taken into account, satellite imagery. All of this still in 1987, the best they could do was just to have phoning farmers or producers and have an intention of crop plantings in the region. In the late 80s, they started to mention computer network to actually be incorporated into forecasting crops or likely crop size. That was then also the spawn of, or the start of the genesis of models like APSIM. The early years for APSIM though. But in the middle 90s, there was a report done by Graham Hammer on using the different approaches, like a regression approach, simple regression approaches, a stress index approach, which is an agroclimatic approach, and also APSIM, the dynamic approach, for predicting likely crop size at the regional scale. And you can see that the dynamic approach had a much less smaller R square than this agroclimatic approach and the regression approach. At that stage, after that report, they've decided to use a agroclimatic approach, which is a crop stress index model, to actually predict the crop size of Queensland and Australia at the shire scale. In predicting the likely crop size, it's important to take into account crop phenology. Now, crop phenology is highly determined by temperature and the way the crop grows over the season, and predicting the crop is most accurate at flowering or grain filling, and then after that. So for us, as, in this domain, that operates in this domain, it's very important to see how far we can actually, how early we can actually predict the crop. And and the earlier you go, the lower the accuracy. And the highest accuracy is actually at the end of the season. But for producers and industry, it's more critical to have a system that actually predict at a very early stage. And that's what we have developed. We've developed a biophysical crop model, which is a function of the year, the time, technology trend, and also the stress index, the SI, the stress index, and also water locking factor. And this is a model that operates at the shire scale. The limitation of this is it doesn't take into account any diseases or losses due to extreme events. But the advantage of this is it's using actual climate, daily climate, rainfall and temperature, simulated on a daily scale. And in this example here, when you forecast the wheat crop, say in the 1st of June, you predict forward with climatology. Then the crop forecast depends then on the ENSO, the Southern Oscillation Index, which you use then to select a subset of years out of the last 110 years. And you produce maps like graphs like this. This is an example from 1994 when there was an El Nino, and you can see the colored lines there is the forecast distribution in the 1st of May, compared to the black lines, which is using no forecast climate indicator. And you can see that the forecast median, which is the orange line, from the 1st of May, it was well below the long-term median, which is the brown line. And there was a phase log on SOI phase 1 in that year, and the likely crop size ended up to be well below the long-term average, one of the worst El Ninos in history for Queensland. Looking at this, the accuracy of this model, this is the R square for the whole of Australia using this model, and you can see the green colors there is 70% and up, so it's very accurate at shire scale for all main wheat producing shires in Australia, and that's the sorghum model. We also developed a sorghum model at this scale, which also has a very tight distribution and high R square at shire level. R's there, and you can see the tight distributions there. Using this in an operational sense, you can see the top one is just for the 2006 season, where we actually predict at 1st of June, which is for most places in Australia, that's around planting, when planting occurs. And then you produce that every month, and you can see the red color there is a very low percentage, below 10% chance of exceeding the long-term median. And then this is for the sorghum model. Again, a different season, different crop, and you can see a high chance of exceeding long-term median. So and these type of maps are getting produced in a monthly report, crop outlook report, that I'm producing every month. And that's how it looks like, and it's downloadable from QAAFI's website. There's various uses of this, apart from exceptional circumstances. We can also then use this, and I've published this work on a paper where we look at the impact of climate variability and chains on the wheat crop in Australia, but also the insurance industry. I'm currently negotiating with the insurance industry. We've developed a product in 2007, but I'm now negotiating with them to actually further this using remote sensing technology also. The next step is for us to actually determine not only what's the size of or the area of the crop, but also can we actually discriminate between different crop types. For instance, in winter, we have wheat, barley, and chickpea, which is your main winter crops. This is an example. These graphs here shows you this is actually data from ground truth. When I drive through the region, I select a few fields, and this is the EVI, which is the Enhanced Vegetation Index from the MODIS satellite platform. And when you look at it at the multi-temporal, you plot that, and you can see the different colors there represent different regions: Southwest Queensland, Central Queensland, and Southeast Queensland. You can see the green for wheat, barley, and chickpea. Those spectral profiles of EVI does differ a lot. And traditionally, from satellite, they will only use 1 day to try to determine crop area. And this approach, we've proposed an approach, a multi-temporal approach, capturing available crop growth through the whole of the crop growing season. And we're going to use this ability now to actually discriminate between crops. In order to do that, we need to be able to reconstruct the crop growth profile very accurately. Crop growth profile as a green up, a peak, and a senescence, to simplify it. To do this, we've one approach, and one that I'm using currently is the harmonic analysis of the time series. We just deconstruct the whole 23 images through the growing season into 3 harmonics and also the average. And using those 3 harmonics, then we reconstruct that. The blue line there is the actual for one season, and then the reconstructed is the green dotted line. You can see it's doing a pretty good job. This is just for 2 examples for 2 seasons for a wheat crop. We've also published that. And then another approach is just also, instead of harmonic analysis, we fit the curve, various curve. In this case, symmetric and asymmetric, and also a pseudo-Gaussian curve. And you can see that although they're very similar, the chickpea, the curve fitting procedure is doing a good job for all 3 crops. The whole idea of this is, instead of using 23 images, which is a lot of information, just to simplify it into a few variables that can be classified and then accurately use that then and determine the accuracy of that on discriminating between crops. The other aspect to this is actually to collate ground truth data. I'll just quickly, we've developed this paraquat system. Quickly show you if I can get out of here. So this is paraquats. So what you can do, I'll just zoom out. So you can see the black points and the blue points. The blue polygons there is actually polygons that has just recently been captured or recorded by agronomists, private agronomists in the field, or farmers. So farmers can use this, or private agronomists, we send it out to them. They register or use this website, and when we zoom in, say to CQ, you can see that the black there is previous fields that has been collated or recorded. And if you click on that one, you probably can yeah, so you can draw some reports on this. The way to capture also here is to say you go add a record, and let's say you can record that just for example, and it gives you the area of that polygon, and you can say OK or cancel. Just say OK. Then you can add a record to that, and it comes up with an attribute table that you can the user can just fill in winter, summer. And you can select your crop. You can say OK. So this is just an example of paraquats. And the advantage of this system is that instead of me driving around in the field trying to collate with a little GPS some fields, we have different people across the country just putting their data in. So there's actually some farmers also using this, collating that. So we've actually in 2 seasons we've recorded more than 500 fields of data. Well, it would have taken me to do that probably free of a lot of time. Just for me to collate say 100 fields of data will take me 2 to 3 days. So this system is a crowdsourcing type of approach that we're using. We're in a process of actually upgrading this whole system and making it more, giving some more data back to the user. But it's very invaluable in a crop forecasting system of determining what area you want is planted where, what crop is planted where. Using that data, then I use that to then discriminate between crops, and also use that then with my crop forecast biophysical model to determine total production. And you can see this map here is for sorghum crops and cotton crops, using that, then you can. I've done this from 2008, 2009. You can also determine the percentage of area to winter cropping over a period, and also for summer cropping over a period. And you can then determine exactly in which region, what is the crop size, and also where's the crop shortage is going to be for specific seasons. Another example there for wheat crop for 2005, for winter crop, barley, chickpea, and wheat. The wheat is the green, the barley is the yellow. And you can see in 2006, which was El Nino year, much less green and yellow in southeast Queensland. The R-square, looking at Queensland, is very high for total production of crop area estimates. For wheat, this is for wheat specifically. Another spin-off of this approach, specifically the curve fitting procedure, is we can actually then determine the sowing date. In this case, early sowing to late sowing in southeast Queensland, and you can also determine the exact day of the peak of the crop growth curve. Another thing we looked at, or area that we investigated, is linking general circulation models with our biophysical models. And in this case, you can see that the accuracy of rainfall, predicting rainfall at the shire scale, is very low correlation, especially early on. And the yield forecast very early on is much higher, greater than 0.885 correlation in most cases. Sorry, that's the rainfall. So this one is greater than 0.65 in most cases. Then the other advantage of a GCM, which is debatable still, but clearly it's only a 1 to 2 month increased lead time on using the SOI signal, which we are currently using. So there's still a barrier, predictability barrier that needs to be overcome. As the GCMs gets more accurate, industry wants at least 6 months before sowing. They want predictability, but that still has to be seen. And hopefully, as GCM accuracies and increases, that can happen in future. New technologies using in remote sensing is to directly determine crop stress. Now, crop stress is just a function of temperature of the canopy minus the air temperature divided by a vapor pressure deficit. And as temperatures increases, the CO2 absorption reduces of the plant at the leaf or the cell level, and also photosynthesis reduces. I've used this approach then in 2 studies, 2011 and 2013. 2011 was in Northern New South Wales for 40 fields, comparing, using this, determining crop stress from Landsat images and comparing it to 40 fields of yield monitoring data at the field scale, at the pixel scale. And also in 2013 in Dalby for 9 fields. And you can see, using that, the crop stress versus the yield, the actual yield, using that approach gets very high correlated, up to R squared of 0.96 of the observed versus predicted yields. And also actual yield versus predicted yield in Dalby for a different season, much drier environment, it was 0.878 R squared. So quite accurate. And this is the type of technology we want to investigate a little bit more, and I've used this now also across the whole of Australia. Use it for MODIS, just for 1 season, and it did reasonably well, R squared of 0.79. This still has to be researched further, and I'm busy talking to ABS, the Australian Bureau of Statistics, and they want to develop this approach and take this approach further in their modeling with their statistical approach. Just recently, with the Center of Excellence in Translational Photosynthesis, which is a 7-year project, which Professor Graham Hammer from QAAFI is leading, and I've got involved in this environment here, where we look at the phenotyping of plant plots, breeding plots, and using the sensing technologies in this regard. We've developed a platform. David Jordan's bought a spray coop, and we're installing oceanoptics sensing, temperature sensing, oceanoptics hyperspectral camera, and also sonar or LiDAR to measure the cover, the height, the crop stress, fluorescence, photosynthesis across temporal scale, and also all the plots. And this is to improve genotype selection, and also lessons learned from this then can be used to increase the accuracy. What we know at the plot level and the canopy level can be outscaled up to regional scale later on. Hopefully, as satellite, there's also as satellite technology is also increased and their spatial resolution increase. I have to say there's also a satellite that David Lobel and Alfred Hewitt is also currently investigating, determining fluorescence. Unfortunately, it's about a 40 kilometer by 40 kilometer scale, but these technologies hopefully will improve at the spatial resolution of that. So in conclusion then, successfully, it's possible, and we've showed it over the last 17 years, that forecasting crop yield and area estimates is highly successful. It's transparent, it's accurate, it has near real-time capability across large areas. We know that we're operating, producers and industry are operating at complex and variable environment, which is likely to become more intense and extreme. Industry using these capabilities will also assist them in enhance their resilience and adaptive capacity in those regions. Integrating remote sensing with biophysical models is doable, and I've showed it here. And the utility will depend on the trade-offs between the risk, the accuracy of your forecast, and also the value, the timing of such an forecast. Future regional application will benefit from what is learned at a planned canopy field level research currently underway. Thank you.